Okay, guys, today we're going to finish activity 11, where we're going to do the day 2 of 11.1 and 11.2. So today we're going to be identifying transformations like we did in the previous video, but we're going to take it one step further and actually graph them on the coordinate plane. So make sure you have the day 2 note sheet for this lesson and something to write with. So let's go ahead and get started. Okay. So to describe the transformations, we first have to talk about what the parent function does. Okay, so remember the parent function for this is going to be a plane f of x equals x squared. So the parent function is the simplest function of that particular type. So remember, when we start doing these problems and start putting numbers in, that's what's going to give us our transformations. So the book had us make a table of values to see what the parent function does. But for the sake of time and for our video, I'm just going to use Desmos since we're familiar with it. I'm going to go to Desmos here, and I'm just going to graph the parent function. Again, the most basic form of the function, just a plain x squared function. So as I can see in this graph, my vertex point is at the origin, and it goes up by 1 on each side. So we have our next point at 1, 1, and then we have a point at negative 1, negative 1. Get it on there. There we go. Okay. And then it would go to 4 because every number would be squared after that. Okay. But the most thing you have to know right now is that the parent function starts at the origin. So this is the point that we're going to be shifting when we start putting numbers into the problem. Okay. So I'm just going to graph our parent function on here so we have a visual to look at while we do our problems. But it goes up by 1 on each side. And there is our parent function. So it starts at the origin, and then depending on what numbers we put into it, that can shift the graph around. So I just want to go back really quick and reference yesterday's video and look at this part really quick. So remember, these are all of our transformations. So coefficients in front are going to change how the parabola looks. It's either going to be a stretch. Remember, the stretch was narrow. If there's a fraction in front, that makes the graph more wide. And a negative is going to flip the graph. Okay. If we have something inside the absolute value function, remember a minus moves it to the right and a plus moves it to the left. So if it's inside those parentheses, that's your left or your right shift. And finally, the k value, if we have a plus k, it moves it up. A minus k moves it down, and that's outside. That's at the end of the problem. So it's outside the squared part. Okay. So let's go back to our graphs now and actually do some. So let's look at number 1, where we have x squared minus 3. So that minus 3 is the only thing that's changing my graph. We have one transformation here. And since it's outside the squared part, this is my vertical shift. So this tells me this graph only goes down 3 units. So if I'm going to graph that, normally our parent function would start at the origin. So I'm just going to mark that with a little x to know that that's where we're starting at. But this graph is going to transform by shifting down 3. And then the parent function just goes up 1 on either side. So just so you get the right shape, you can do that. And there's our parabola. So make sure it's a U shape. It's got a curved bottom, and we should be good to go. All right, let's look at the next one here. We have x plus 4 squared. So that plus 4 is inside the squared part. So that's your left or your right shift. And if it's a plus, that's going to move the graph to the left. So we're going to go left 4 with this graph. So again, the parent function normally starts at the origin. So from the origin, then I'm going to shift my graph 1, 2, 3, 4 to the left. So here's my new vertex point. Again, on either side, it goes up by 1. And we make our curved shape here. There's our parabola. So it's a lot faster than the other way we learned to graph. If we know our transformations, then all we have to do is just a quick shift. You just have to remember the rules, and you should be good to go. All right, number 3, we have a 2 in front. That's our only transformation. So this graph does not go left, right, or up or down. So it's going to stay at the origin because there's no plus or minuses here. All this graph is going to do is have a stretch. Okay, it's going to be narrow by a factor of 2. So that means all your numbers get multiplied. But let me just show you the quick way to do this. Normally, we would go up by 1 on either side. But if you have a shrink or a stretch, you're going to go up or down by whatever coefficient is in front. So since it's positive, we're going to go up by 2 on each side. Up 2. So now when I connect my dots for my parabola, you can see that this purple graph is a little skinnier. It's more narrow than the 2 previous ones I did. Okay. Let's do one more together, and then you guys are going to try 5 and 6. So number 4, I have a negative in front. So as soon as I see a negative, I know I'm going to have to flip this graph. So a negative, we have a flip. And then I see a 1/2 in front. So anytime we have a fraction in front, remember that makes the graph more wide. So we're going to be wide by a factor of 1/2. So again, there's no plus or minuses here, so we're not going to shift it left, right, or up or down. So my vertex is staying at the origin. We just have to flip it and now make it wide by a factor of 1/2. So if it flips, that means it's going to open down. Okay, so I'm going to put my points below my vertex. And that 1/2 just tells me I'm going to go over and down 1/2 on each side. So that coefficient, anytime you have a shrink or a stretch, that number is going to tell you what you do on either side, how far you go up or down. So remember, the parent function just goes over and up by 1 on each side. So this is going to be 1/2. And you can just eyeball the 1/2. It doesn't have to be perfect. But there's that graph. So if we look at and compare these, you can see how that orange graph is much wider than the previous ones that I did. So make sure if it's supposed to be narrow or wide, it looks that way. Okay, let's move on now. We're just going to do 4 and 5. So I'm going to have you guys try this one. So let's look at 5. X minus 1 squared plus 5. What are our transformations on this problem? So there's 2 transformations here. I see 2 numbers in the equation. So what do those do to our graph? Well, hopefully you said that it's going to go right 1 and then up 5. So if that happens, our graph should look something like this. Now it went off the graph a little bit, so that's why it looks a little funny, but that's what we get. All right, let's look at number 6. We have negative 4, x plus 3 squared, and then plus 2. So everywhere we have something changing in our equation, we have a transformation. So I see 1, 2, 3, 4 transformations on this one. So what are those 4 transformations? So start with naming those. Here's what I got. So it flips because of the negative. It's going to be narrow by a factor of 4. We're going to shift left 3 and up 2. So I'm going to have you guys try this one. See if you can graph this one on your own. Okay, if you did it correct, this is what my graph looked like. So if I go left 3, so remember our parent function always starts at 0, 0. So there's 0, 0. So I'm going to take my function and go left 3, up 2. There's my vertex point. And now I can flip it. So I'm going to go down, and I'm going to make it more narrow by a factor of 4. So that means on either side, I'm going to go down 1, 2, 3, 4. And it's flipped, so make sure it's opening down. And there's your parabolas. So if you know how to do transformations, you know how to do the graphing. So again, we always start at the origin, 0, 0, and then move from that point. If there's no transformations, meaning no left, right, up, or down, there's no pluses or minuses in the problem, like numbers 3 and number 4, you stay at the origin. You just do your shrink or your stretch. Okay? So let's flip it to the back side now. We're going to look at kind of doing the reverse. So we're going to start with the graph and describe the transformations. and then use that to write the equation of the function. Okay. So remember, we can always use our vertex form for these. So this vertex form, let me highlight really quick for us right here. Okay, remember the vertex is the h and k. So if you know what those values are, you can just plug them in. Okay, but let's talk in more terms of transformations. So here is my vertex. Remember, the parent function would start at 0, 0. So it looks like all this graph did was go down 4. Okay, so I don't have any left or right shifts, so there's no h value, so there's nothing in parentheses. But if it goes down 4, I know that's a minus 4 for my equation. So here would be our function, y equals x squared minus 4. Okay, let's do another one here. So we have our parent function who normally starts at the origin. Compare that to what this graph did. So from the origin, it looks like it went to the left. Looks like it went left 2. So remember, our left and right shifts go in parentheses. So left was x plus 2. It didn't go up or down at all, so I have nothing else on the back end. So there's your y equals x plus 2 squared. And again, if you forget when do you use a plus and when do you use a minus, go back to this kind of part, so the day 1 note sheet where it tells you what everything is. Okay. So I'm going to have you guys try these bottom two, numbers 3 and 4. So these ones are going to have 2 shifts, if you can tell. Okay, this one goes to the left, and it goes down. So how much did it go over, and how much did it go down? So put that into your equation. So give that one a try, number 3. Okay, it looks like it went left 4 and down by 1. So if that's the case, your equation should look like this. X plus 4 for the left and minus 1 for the down. Okay. One more of these. Let's look at this one. There's my new vertex. So remember, it starts at the origin. So how did it shift? Looks like it went to the right. And then it went up. So just count how much it shifted and use that to write the equation for number 4. Okay, I can see that it looks like it went to the right 3 and then up by 3. So if I had to write the equation, it should look something like this. Okay. So knowing your transformations will help you write the equations. Just got to know your rules, when to use minus and when to use plus. Okay, we're just going to finish up here with doing ones that are shrinks and stretches. Okay, so you can see they're all at the origin, so we don't have to worry about going left, right, up, or down. So there's our vertex at the origin, and at the origin. So if I look at number 5, I can tell this graph is more narrow, meaning more skinny than the parent function. So we know we're going to have a coefficient here. So it's going to be something x squared. So we just have to figure out what that coefficient is. So one trick you could do is you could plug it into this equation. So if you pick one of the points, you plug it into y equals ax squared and solve that for a. So what I mean by that is if I take, let's say this point, 1, 3. Remember, your ordered pair is x, y. So y equals a times 1 squared, ax squared. Well, 1 squared is 1, so we get 1a equal to 3. So that's your coefficient, your a term. Now you could also see that on either side of the vertex, these points go up by 3 on each side. So you can also do it by looking at the graph as well. Okay, let's try number 6. This graph is noticeably wider. So remember, when we have a wide function, that means we have a fraction in front. Can you guess what that fraction is going to be if you look at these points here? Hopefully you thought that it's going to be a 6th. That'd be 1/6 x squared. Again, I can take that ordered pair and plug it in. So y equals a times x squared. So actually, I was wrong. This is 36a. So this would be 1/36. Let's try one more. I'm going to have you guys try 7. Okay. So if I use this point, -2, -2, plug that in and see what you get for the A. So you're going to get something x squared. So see if you can figure out what that A term has to be. Okay, here's my work that I did. So I plugged in the x and the y. So -2 squared gives me a positive 4a. So if I divide that 4 in front, I got -2 over 4, which would reduce to -1/2. There's your equation. Okay. So let's look at everything together now. If it shifts from the origin, you just have to count how far it goes left, right, or up or down. If the graph looks noticeably wider, then you just kind of have to plug your x and your y into like the general formula to see kind of what's happening with that a value. How is it kind of multiplied by? Okay, so there we go.